It's just me. That's the way I see it. What? It's just me. Okay, actually, like Porter. It was so fun, like, yeah. They were really. That's how. Yeah. And then I saw. Only on your. All right, guys, page 50. Okay, just 50%, please. I don't know. Yeah. Okay. This is basically the last section for this unit. But this will take a little bit of time to kind of get comfortable with. So we'll take our time with this. We'll continue talking about polar area between two or involving two polar curves further on Monday, and then we'll do review Tuesday. Then we'll have a more than a week to let this sink in before we take our test. So we know that area of a polar curve is 1/2 depth to integral from a to b of r squared d theta. Now, when we're dealing with more than one polar curve, things to watch out for is points of intersection. Sometimes the points of intersections are kind of hard to find in polar form. So I'll show you different ways that we can find points of intersection. One way is we can do it algebraically, use inverse trig. The other thing that we can use is we can put it into rectangular form and just graph the rectangular versions of the curves and then just look for the intersections, even though it doesn't look like this, but the intersection can be found, I think, more easily in rectangular form. And then also symmetry can play a huge role in terms of, if we know that there's symmetry, then we can save a lot of time because rather than trying to find the area here, area there, if we know that there's symmetry, we can just find the portion that we need and then just double it or triple it depending on what we're looking for. So number one, find the area of the region common to the polar curve of r equals 4 cosine theta and r equals 2 sine theta. Now, I wanted to blow this graph up so that I can kind of show you all the different parts of arriving at this area. So I put this graph on the next page, page 51. So I filled up the whole page here. So I think so that it feels a little bit easier to kind of talk about these graphs. So page 51. Now, I want to use a highlighter here just so I can have an easier time kind of highlighting what I want to go over. So first off, we have r equals 4 cosine theta. That's this the circle that is centered at 2, and cosine is symmetrical about the x-axis and has a diameter of 4. I'm going to use red for cosine for this curve here. You don't have to highlight it. I just want to do it for demonstration purposes. So here's I'll fill out the rest later. Next up, r equals 2 sine theta. That's the one that is symmetrical about the y-axis here. I'm going to use green to highlight this one here. let me start off with the point of intersection. So the point of intersection, we can do this algebraically. So I'm going to set these equal to each other and then look for that intersection algebraically. So let's do this. For cosine theta is equal to 2 sine theta. I have an easier time thinking about cosine and sine if I can just convert it to in terms of tangent. So what if I do this? Just divide both sides by, divide both sides by, so I get 4 is equal to 2 tangent theta. Therefore, divide both sides by 2, and therefore 2 is equal to tangent theta. Now I'm going to use my calculator here. Tangent theta equals 2. This is not going to be a nice unit circle value, but as long as I'm in radian mode, and if I do inverse tangent of 2, I should be able to solve for theta. I get 1.107. So that's my intersection here. Everything's in terms of radians. So theta is 1.107. Now, the way that we find area, or the way that area is found using polar, it's not just, oh, this curve minus this curve, and then just find the area of top minus bottom, right? It's not quite the way that polar works. Remember, the way that polar area works is that all the area regions starts at the origin, right? So it kind of extends out in these sector shapes, or in these sector patterns in counterclockwise direction. Okay, so initially, when we find area, it's going to start hitting these curves. So initially, which graph is involved in this process? Which one? Is it cosine or is it sine? Sine, right? So I just wanted to show the green to indicate that, initially, as we move around, we're not hitting the because okay, so our goal is to figure out ultimately the shaded region, right? But the way that this accumulates, it kind of starts at the origin and it kind of just builds out, it kind of extends out. So you guys see that initially, when area is found, it is not touching the cosine. It is hitting that the sine, at least all the way until we hit that theta. Are we good up to that point? So then there's a dividing line, right? There's a dividing line. But then after it hits that intersection, what graph are we seeing? Now we're seeing for cosine theta, right? So now it just continues to extend out, but it is hitting the other graph until it reaches this point here, which is at pi over 2, because we know that cosine theta will start here at 0 and goes to pi over 2, and then it'll fill out its entire cycle from 0 to pi. So then my area is broken up into 2 definite integrals. The first is this green region, right? So from 0 to 1.107, all we're doing is we're just accumulating area from the 2 sine theta graph. So we'll just create an area formula for that portion. 1/2 integral of r squared. Remember, we're starting with that 2 sine theta, right? So 2 sine theta quantity squared d theta. So this will take care of this region in green plus 1/2 integral from 1.107 to pi over 2. So the remaining portion is going to be involving the red graph, which for cosine theta. Does that make sense? I think if we treated this like rectangular, we may be tempted to say, oh, it's just top graph minus bottom graph, and I'll just do the same thing that I would with area for rectangular graphs. But the way that area is found is counterclockwise, and it accumulates these regions in this direction. Yeah. Oh, over here, because this graph in red, this r equals 4 cosine theta. Let me just show a couple of order pairs here. So at theta 0, it's going to be 4 cosine of 0, which is 1. 1 times 4 is 4. So this graph starts off here. Let's say at pi over, okay, and then at pi over 2, what's cosine of pi over 2? 0. 0 times 4 is 0. So then at pi over 2, now normally pi over 2 would be up here, right? Pi over 2 will be up here. But at pi over 2, the graph is going to be at 0. So it's going to end up here. Yeah. So, so this circle is going to complete this full cycle from 0 to pi. I think for like limacons, for petals that have 2 theta or 4 theta, those will take longer. Those will go 2 pi, but these circles will complete their complete cycle from 0 to pi. So by the time we reach here, the red curve is only getting to pi over 2. Okay. So then let's practice plugging this in our calculator. We should be able to arrive at an area that is 0.9617. And again, you can do all this in rectangular form. You don't have to get that polar form to show up with a theta to find our area. I just want to show you that we can also find the intersection between 2 polar curves more easily by graphing them in rectangular form. So if you graph it in rectangular form, you know that the intersection is occurring in the first quadrant there, and I can just find my first case of intersection in rectangular form and do second trace, intersect, and pick points close to my intersection. I'll get the same thing, what's right, x is 1.107, which is the same thing as the theta we're looking for. I think it's a little bit harder to get the intersection information to show up when you're graphing them in polar form. Okay, any questions? So think about area as extending from the from polar zero in these sector regions, and it's going to kind of fan out in the counterclockwise direction until we've reached the full area that we're looking for. So any area region that we're looking for always has to include the origin, the polar zero. All right, back to page 50. Let's look at number 2. All right, find the area of the common region to the polar curve r equals 2 and r equals 2 minus 2 sine theta. So we know that r equals 2 is going to be the circle. R equals 2 minus 2 sine theta, that's going to be the cardioid or the limacon. That's the one below here. So the common area is going to be what is shared, the intersection between the two curves. So let me just highlight very lightly where that region is. Okay, so ultimately, we're looking for that shaded region. Now I'm going to start at 0 and build my way out. So I'm going to sketch the graph here again. So this is the first part of my shaded region. I'm going to start at 0 and I'm going to extend out initially just with this portion. I'm going to kind of break it up into 2 regions here, because the first region is not going to include my circle, right? It's just going to include my limacon with that portion sticking out. So this is going to extend from 0 because for the 2 minus 2 sine theta, at 0, my graph is going to be at 2. So it's going to start here. And then at pi over 2, 2 minus 2, well, we know that sine of pi over 2 is 1. 1 times 2 is 2. 2 minus 2 is 0. So it's going to hit this region at pi over 2. So we know that for this upper portion, that is where from the polar 0 is hitting that bump there, is we're referring to that 2 minus 2 sine theta. So we have an integral that we can represent with that region there. So from 0 to pi over 2 of 2 minus 2 sine theta, sorry, 1/2 in front, squared d theta. So let me highlight here. This region is only taking care of this little portion there. Now, as we continue to kind of go around the circle here, this region is not going to get touched on by theta until we're in that 4th quadrant, right? So we can either go from 3 pi over 2 to 2 pi, or we can go from negative pi over 2 to 0. Okay. Either negative pi over 2 to 0 or from 3 pi over 2 to 2. Either way, we know that we want that region, this region, to be with the circle. So if I want to go in the negative region, I can say negative pi over 2 to 0 for this region. Or, but again, you can just as easily say from 3 pi over 2 to 2 pi. But that region is going to be 1/2 depth integral from negative pi over 2 to 0, r squared, d theta. That is going to be 2. Now you actually can do something with this where you don't have to go through polar formula, because this is a nice predictable shape, right? It's got a circle. This is a quarter circle. You can just take area of a circle, divide it by 4, and that'll get us the same value. But either way, we're going to add these two together. Oh, my bad. It says find the area of the common region. Did we find all the common region? No. Okay, so there's another half that I did not include at all. But the advantage here is that if we can just focus on a portion, then we can just double it rather than having to find the area, all, going from 0 to pi over 2, and then from, pi over 2 to 3 pi. It feels like a lot more work that we don't have to do. So if I can just figure out a half of my region, I can use symmetry to double it in the end. So my area is just going to be this. I'm going to double my final result. Any questions with 2? Yeah.
For the integral of 0 to pi to get both sides.
Yes, you can go from 0 to pi under the 2 minus 2 sine squared theta. And then from here, you can go from pi to 2 pi, and then get that area. Is that what you want? Yeah. So if you want to find the full region, you can. I'm taking advantage of symmetry here. I'm just finding half the region and doubling it. But yeah, double check though. See if you get the same answer with the way you do it. You should. But if not, we can go back and look at it more closely. But that should be right. All right. Any questions with 2? All right. Number 3. Find the area of the region common to two polar curves. You got r equals -6 cosine theta. You know that's a circle, so that's going to be the one here. And then you have 2 minus 2 cosine theta. With this setup, you know it's going to be a cardioid. That's going to be the heart-shaped graph there. Let me highlight the axis here. All right. Area common to it. So yeah, I prefer to just find half of my diagram and then just. So what's common is the intersection between the circle and the cardioid. Okay, we're talking about that region there, right? Okay, let's go ahead and find the intersection. I'm going to go ahead and just solve and find the intersection. See if I can do it by hand. So it's a nice unicircle valley here. Where's cosine equal to -1/2? It's going to be in that pi/3 family. Okay, but I really only have to worry about 2 pi/3 here because 4 pi/3 is down here. I'm just going to focus on half of my diagram. So there's a split, right? There's a split. I'm going to draw a line to indicate where that split occurs. Okay, remember, we're building out our graph in a clockwise order. So it's going to start here. It's going to start from. So this region here, what is this touching? Is this touching the circle or is it touching the lemmason or the cardioid?
Circle.
Circle. Okay. So the circle is going to be from 0 all the way until 2 pi/3, right? 0 until. Oh wait, I'm sorry. No, not 0. If we think about -6 cosine theta, this is building out a little bit different here because of negative. So just get some idea as to where is this graph beginning here. So at 0, it's over here. It's over here at -6. And then at pi/2, it's not going to hit a polar 0 until pi/2. So at this stage, this part of the graph is from pi/2 to 2 pi/3. See that we're starting here, but this polar 0 doesn't begin until that pi/2, at least not for the cosine graph. So for the cosine portion here, area sub 1 is 1/2 integral from pi/2 to 2 pi/3, and then my circle -6 cosine theta squared theta. So this is my region in green. after this intersection, then it hits a different graph, right? Then it's hitting the lemmason or the cardioid. From 2 pi over 3 all the way to pi. We know that with the lemmason or with the cardioid, it starts at 0, goes to 2 pi, and then it completes the cycle from 0 to 2 pi. So pi would be the ending point here for. So my second area region is 1/2 integral from 2 pi over 3 to pi, and this is now hitting my cardioid. This is my red region. Okay, so when I put this in the calculator, I add this together, I still have to do what with my sum here? So it's not even the calculus that's going to potentially trip us up. It's just understanding, when is theta going to actually hit the portions of the graph that we're talking about, and understanding that the area is formed extending out in these segments or in these sectors from the origin, right? It kind of builds out in that direction. Sorry? Oh, the axis. Yeah, I should have drawn, this should have been drawn a little more clearly. But we know that with these graphs, the polar zeros, it's going to be right at the polar zero. So that's my hint there. But yeah, the axes are not as clear as it could be.
If you want to find like all of the area for the -6% beta without doubling it, could you do like -5/2 as your bounds?
Let me see. For which region? For the,
The blue one.
okay. What did you say? From where to where?
-5/2.
So yeah, so -5/2, I don't think would be a good fit because the intersection down here is at 4 pi/3, which if we were in the negative region, subtracting 6 pi/3, it'd be -2 pi/3. But then from -2 pi/3 to from -pi/3, pi/2 to 2 pi/3, that will get us that full region. So if you wanted to go, you want to do this, it should work. Sorry, maybe 2 pi. Oh, wait, I'm sorry, no. This is at 0. More than one side of it. I think it's off with my theta. Let me come back to that. I'm getting lost here with where that intersection is. Okay, so let me. Okay. But yes, we should be able to find the area without having to rely on symmetry, but I like symmetry because then there's just less regions to think about, less bounds to think about. But yeah, let me think about how we can get to that area without having to use symmetry. Okay, last thing I want to talk about is just the formula of area bounded by, if we have a polar curve where there's one inside the other, and let's say we have two strange, well, yeah, this graph is just drawn in a different way here. But let's say this is R sub 2, this is representing some R equation that's further out. And then let's call this one R sub 1. So R sub 2, I'll use green, and then R sub 1, I'll use red. Now let's say I wanted to find the area of this region that sits between. We can't just say, okay, it's going to be R1, so R2 minus R1. Or we can, but the thing is, it's going to give us this region. It's not going to give us this region here. So essentially, when we find the area, we're going to be finding the area of this larger region first. So we're going to find the area of the entirety of this entire region. And then we're going to end up subtracting the region involving R1. So then if we take the entire, remember, every area we find has to include the origin. We can't just go ahead and find the area here. We have to find the full area first, then we can subtract out the part that we don't want, and then we're left with this region. So that formula is going to be 1/2 integral from a to b of R sub 2 squared d theta minus 1/2 integral from a to b R sub 1 squared d theta. So if I want to find the region between two curves, I need to find the region of the larger area and then subtract out the area or the region that's closer to the origin. All right, your homework is just to make some progress with our polar problems, our polar area problems. So page 48 to 53. And then we'll continue. Yes, we've covered pretty much all our new topics. We're just going to get practice starting next week. All right, come get your phones. So it's on the track. So I think, if we divided about 9 events. But then it slow down to sign 0. And both.
There's like time delay.
Yeah, basically, it's like, I think we're losing the solution, but
Right, yeah. Right, and I strict.
There's a slowdown period.
Yeah, it's slow down. Yeah. Like it's like real life. In real life,
Yeah.
you can't 5 meters. Yeah.
I can do that when it hit a tree.
Yeah.
This Africa.
It's a graph thing you've ever studied.
Yeah, we got
Yeah, I can do that when I hit when I'm riding the bike. Then I just the process.
That's interesting. I always thought.
So I gotta like scratch this. I'm training in April.
It's like everything.
Yeah, like with people. Yeah, and you never even got masters.
Involve the origin.
One of the things I got you.
That polar down. That indentation is going on. Always start. You can't just say, oh, you can't just say. But every area of the possibly has to play out.
Clear this thing out. Crazy. What I'm doing is like so clearing out regularly, but I'm keeping all the notes. Yeah, it's not about like I know that I
I just keep them at home in the file.
yeah, but I'm afraid if I do that, I'll just like forget where I put them and just like not have any of them at all. Not that like notes are even good, but like
Yeah, because we kind of can count that. For the intersection, this one, rather than relying on.
like
Yeah, for me, I was like, I wasn't gonna worry about this. Yeah, I was, yeah, because that, like, you're right. This, that's. But what about the other? This one here. Was that, I thought that was 4/3. It's 4/3.
Power 2, 2 power 3. Power 2.
That sounds.
It goes like the other.
Yeah. But that's for the circle, right?
And for its middle,
This question was, how can we represent the area of a circle?
But you're using.
Intervals.
That's crazy, you're like 4 year old.
And so let's get it. Just
Yeah.
get this before through, because the circle is not a cycle. Zero to pi. So that's power of 3 is an outside. Unless you start at 2 pi over 3.
Oh, yeah.
Yeah,
It's not.
I think the problem is that we're trying to find.
I know, it's actually.
There's a different.
Yes.
A different.
Because it is practice.
But even if they don't intersect, we should be able to know where that is.
Is it good? I've never tried. I think like this, we can only find the intersection.
My grandma was talking about how it's no do. Yeah. And then what my mom loves diagnosing my children. I was like, why don't we? And she was like, one day, all the people that have a friend.
Yeah.
Yeah, I gotta think about this sometime. Thank you. I appreciate it. Have a great weekend, guys. Bye, thank you.
Yeah.